So what I'd like to do now is, and this let me see, I'm actually going to play something for you. So Gary Stephenson recorded something, and let me see. Let me read you my write-up for this. Is faster than light communication possible? Gary Stephenson discusses quantum entanglement, quantum signaling, and emerging research in superluminal quantum communications. So Gary's going to be addressing the no communication theorem, the no teleportation theorem, the no cloning theorem, and exploring possible methods to circumvent the speed of light to facilitate the development of superluminal quantum communication technology. He's going to be talking about the Canary Island long-range quantum state teleportation experiment, quantum spin liquids in Herbertsmithite, and entangled photons in orbital angular momentum twisted beams. So we recorded this actually ahead of time. Gary has another event, he's traveling, and so that's kind of what came out of this. If I can give you guys just a little bit of background info on this. This started to, I'm pretty active on LinkedIn. Gary's on LinkedIn, a lot of folks are. And on LinkedIn, there has been more and more hubbub about quantum communication and quantum computing, right? And as many of you guys know, China has done some recent experiments on it that are pretty big. The US government and US universities and private sector have been starting to work more in quantum computing, and quantum communication is not far behind. So one of the things that came out of that was quantum entanglement happens instantaneously. And I'd always believed, this goes back quite a ways, I'd always believed that, okay, well, if quantum entanglement happens instantaneously, that means you can communicate with it instantaneously. So there were some papers, it turns out, that have said otherwise, that even though the entanglement happens instantaneously, the communication itself, because of the way it's measured and transmitted, is still subject to relativistic speeds, right? And so basically, Gary came up with this presentation to kind of provide some possible ways around that, and to look at ways that might not be true. You know, one of the things that I've kind of looked at in terms of the arguments against instantaneous communications is that they do seem somewhat dogmatic in nature. They kind of fall back on logic that may not be the most sound, probably just to preserve C from the relativistic world, even though that doesn't necessarily apply in the quantum world. So I've got his video queued up, and what I'm going to do is I will play this for you guys, and let me know if we have any issues with it.
Okay, thanks again, Tim, then, for giving me this opportunity to share this. I've given this talk a couple times, once in 2012 at a Bill conference, and once in 2014. I added the part 2 in 2014 for an ISDC conference, which is hosted by National Space Society. Their interest, of course, is in space, so I added possible applications to Mars missions when I presented it to them. A lot has happened, obviously, in the last 10 years since I originally wrote this paper. So I've lost the original charts, the PowerPoint charts. All I have is the PDF. So I wasn't able to make changes to the PDF. But what I can do when I reach a critical spot is jump into some of the updates that have been occurring in the quantum entanglement area. So I'll handle it that way. Well, why a quantum entanglement talk, and what triggered my interest in 2012? It was really a series of pretty surprising experiments that triggered my interest here. That I'm an engineering person, engineering background. I have my undergrad degree is physics, but I've worked most of my life as an engineer. So I like to approach things from an engineering point of view. So when I start seeing that there's real engineering impact to quantum entanglement, that's what gets my interest. Not so much the physics, more of just the potential applications in engineering. So the three that got my attention, which I will cover in this talk, is the Canary Island long-range quantum state teleportation experiment. There's a quantum spin liquid in Herbertsmithite experiment that was also announced in 2012, I believe, by MIT. And then there was a pretty astonishing paper on entangled photons in orbital angular momentum twisted beams. So I'll talk a little bit about that one. Why is this interesting? It may be possible to apply quantum entanglement to action at a distance type applications, such as frequency time standards, communication, potentially quantum entanglement communication would be incredible because we wouldn't have to worry about R² loss like we do with electrodynamics or electromagnetics or even gravitational waves. Power coupling, I'm not so sure about. I thought at first using OEM beams, we might be able to do power coupling. Subsequent conversations I've had with people indicate that's probably not the case. I'll go over why it probably won't work and what might work instead. So the first part is the part that I originally presented at Bill Conference, which was just to talk about the experiments that have been going on. But before I jump into the experiments, I wanted to go over a real brief description of what is quantum entanglement. Quantum entanglement is fundamentally a coupled set of quantum states. It's where more than one particle shares the same exact quantum state or qubit. So that can happen at any distance. Distance sort of doesn't matter with quantum entanglement. They can start out being entangled by the same signal, and then they can be separated, but they stay entangled unless something happens, like a measurement happens, to decohere them. So essentially, quantum entanglement is a shared quantum state, a source of quantum coherence. If you have a large number of particles that are all entangled, that's called quantum coherence, and that is, from an engineering point of view, more useful than a single qubit. Now you've got a large array of particles that share in the qubit versus a single particle, and with that you can start doing engineering. For instance, quantum computing, and most of the changes that have come out in the last 10 years are driven by the quantum computing people. And so that's really a group that you want to track if you're interested in quantum entanglement. So there's quantum coherence that's coming out of it, and this could lead to novel behavior, much as we see novel behavior coming out of superconductivity and superfluidity. And then it's also an example of non-locality, because when you change, if it's a shared qubit, when the quantum state is changed in one location, it changes in the other location. Sort of a macroscopic example of this, they're not really particles, is Schrodinger's cat, where there are two quantum states. Either you have a particle that's decayed or it has not decayed. And in the experiment, you put this poor cat in a box, and there's a Geiger counter that measures the decay. If the Geiger counter gets tripped, it trips a hammer that breaks a cyanide vial, which kills the cat. So essentially, there's two different states that can happen here. There's the live cat, which is correlated with no decay and a not broken poison, or there's the dead cat that's correlated with the broken poison and the decay. So when you go to measure and you peek in the box, is the cat alive or not? You are selecting whether or not there is a decay or not a decay. There is a superposition of those two cases until you peek in the box. Now, this is a good time to break away and cover other recent developments in this area. And I'll leave this on the screen for people to look at. That's going to be my supplemental material that's happened between 2013 and today. And one of the papers I want to pull in is Susskind 2016. It's a theoretical paper. The rest of these are experimental papers. But Lenny Susskind did a really good job of describing this very case in his paper that compares the Copenhagen interpretation of quantum mechanics with Everett's interpretation of quantum mechanics. And the paper is entitled ER equals EPR. Well, what does that mean? EPR is the physicist way of saying quantum entanglement. It stands for Einstein, Podolsky, Rosen. Those are the three guys that wrote a paper saying, hey, quantum mechanics doesn't make any sense because if it did, then you could have non-locality or spooky action at a distance. So they were actually detractors to quantum entanglement. And they thought, here's the problem with it, is you could have non-locality. which turns out to be the case. So here's a quantum mechanical effect that's named after its detractors. So when you see EPR, it means quantum entanglement. When you see ER, the same 2 out of the 3 dudes, Einstein and Rosen, also worked in general relativity and also dreamt up wormholes. So when you see ER, an ER wormhole is it's a solution to space-time that allows for a wormhole. So what Lenny Susskind is saying here is that quantum entanglement is an information wormhole. That's all it is. So he goes over that in his paper here. And it's, I think, a really solid, good way to look at, is it really action at a distance? Is it really non-locality when it's an information wormhole? So here's your information wormhole, your EPR entanglement. And here's an actual wormhole where you've got curved space-time, where the space-time dimensions are also participating in the wormhole. That's an Einstein-Rosen bridge, or a wormhole. So he's saying ER is EPR. Okay, so that's the first clarification. So that think of quantum entanglement as an information wormhole, number 1. The second thing he goes about saying is that the interpretation, the Copenhagen interpretation that the waveforms are collapsing is not supported by the evidence, or even by the theory in terms of being self-consistent. You can look at the Copenhagen interpretation and the Everett interpretation as a collapsing wave function here, where you take a measurement, collapse the wave function, take another measurement, collapse the wave function, and so on. Or you can look at many of these possibilities exist, and you're just going down one path. It doesn't mean the other possibilities have gone away. It doesn't necessarily even mean there's many worlds. Everett himself hated the many worlds interpretation of his theory, so that's why Lenny says Everett instead of many worlds. But what it doesn't show here, and what Lenny Susskind is pointing out, what they should be showing is some of these branches can come back together again. You can wind up with situations where you're right back to where you started with enough measurements, especially if a measurement is reinforcing an original measurement. So basically what he's saying is there's only one system in the Everett interpretation, and the user, the observer, is part of the system. This view that the observer is outside is not an accurate view. He proves this with Schrodinger's cat again. You have Schrodinger's cat, you have Wigner's friend and Wigner. Wigner's friend measures the cat's situation, becomes entangled with that cat situation, and he communicates it to Wigner. Excuse me. Einstein then is observing this entire thing. And so all 3 of these are entangled, both observers and the cat. He shows this in his paper as this connected surface here. And that entangled connected surface can be described as what they call a GHZ, stands for Greenberger Horn Zellinger entangled tripart state. You can go through a measurement series in that state and reconnect with an earlier entangled state. So that leads to the Everett interpretation. So I just wanted to point that out as a little expansion on Schrodinger's cat here. Okay, hard for time. Okay. So the experiments themselves. First one was the Canary Island experiment. It's an experiment where there were 2 entangled photons. One was sent to a different Canary Island. The Canary Islands were 89 miles apart. And when they changed the state on one photon, instantaneously, the spin state changed in the other photon. Instantaneously. And they measured this with a classic channel. So they were able to compare the timing and see that it was not only faster than light, but without even the smallest of delays that they could even bet within the measurement error, which meant it was really altered instantaneously. So this was very important because it really proved without a shadow of a doubt action at a distance. Another one was observing a quantum spin liquid. What's a quantum spin liquid? Well, it's the spin states. It's a solid, Herbertsmithite is a solid crystal, but the spin states act like a liquid. They kind of slosh around. And you can interpret, you can actually measure, I should say, the spin states with neutron scattering. And it is possible to develop a coherent spin state set in Herbertsmithite, where you have some spins that are up, some are down, but they're all coherent. They're all a giant single qubit. They're all coherent. And it looks almost like a Bessel function when you're looking at it. And so you can see this kind of hexagonal pattern that they're imposing on this Herbertsmithite. And they measured it for the first time using a neutron scattering, the spin excitation. So what this says is, if you change the spin excitation in one part of the crystal, the entire crystal changes instantaneously. So you can use this then as one single piece of, one giant piece of qubit. The third experiment was twisted light. Twisted light is where the photons are in these very high angular momentum states, where they're basically spinning, or they're spinning very fast. So it's like they're twisting. And if you can use a spatial light modulator to create these modes. So I thought, if they're twisting, each of these nodes is twisting, can that lead to an overall physical twist? Because in meteorology, there's this thing called the Fujiwara effect. And the Fujiwara effect is when you have two cyclones that start getting close to each other, they're spinning at the same in the same direction. The closer they get, the more they tend to spin around each other. That's the Fujiwara effect. And that has been observed with twisted light, because twisted light is light traveling through space or through air. It's a sort of exhibits hydrodynamics. And so they have seen this Fujiwara effect where twisted light can start twisting around. So if that's true, we could use it as a fiber optic spanner. There's a little picture in the bottom here of what a fiber optic spanner is, and it causes things to twist. Now, this particular fiber optic spanner has laser beams pointed slightly offset, and these laser beams are pounding this little thin in the middle, and that's what's causing the thin in the middle to spin. However, you can also imagine using twisted light to cause this Fujiwara effect, where you can start twisting the light, and then that can impact an object and potentially twist an object. So that was astonishing to me as well. Those were 3 experiments that happened in 2012. So that kind of summarizes the part 1 of the story of these 3 experiments, all 3 of which deal with quantum entanglement and exhibit it macroscopically, where you can really see it. Second part was, how might we apply this from an engineering perspective to problems that we have? And when I first gave the paper, of course, ISDC was the audience. So it's applications to Mars missions in this particular case. So what I wanted to dispense with before going over possible applications are some of the theorems that have been perpetuated and I think over applied, and talk about why these theorems may not necessarily be blanketly applied. You have to be careful how you apply these theorems. There are theorems about where quantum entanglement doesn't work. I call them the no-no theorems, or negative Nelly theorems. These no-no theorems are no teleportation, no communication, no cloning. So I'm going to go over those. And then I want to go over, okay, we can't do things in that way, but are there still ways that we can use quantum entanglement that could be useful for applications such as communication? First is the no teleportation theorem. It says classical information channels cannot transmit quantum information. By transmit, we mean with full fidelity. Well, that's true for classical information channels. That's not true for quantum channels. So for a channel that's carrying a quantum, like a fiber optic that's carrying an entangled photon, you can entangle two different locations with an entangled photon. So with quantum channels, you can achieve quantum teleportation, number one. Number two, the Canary Island experiment, which I'm showing here again, proved that. So yes, you can have teleportation, just not over a classical information channel. So people over apply this all the time. Hey, you can have teleportation. Yeah, not over a classical information channel, but you can using a quantum channel. That's number one. Number two, no communications can be achieved on a single shared entangled state. Therefore, shared entanglement cannot be used to transmit any information. Well, there's a counterexample to this, and it was published in 1999 and was called Begging the Signal Question by Peacock and Hepburn. Essentially what they're saying is all of the criticisms about communication are from oversimplifying the problem. So if you have just one photon, for instance, and you use that one photon pair to entangle Alice and Bob, then yes, you will not be able to use that one photon to send any new information between Alice and Bob. But we go to the actual paper. All the criticisms, no signaling proofs, are question begging. They depend upon assumptions that already assume that are so simplifying. They already assume basically that the dynamics aren't there to support communication. So they undertook to examine these no signaling proofs and found them to be fallacies. So that's a good paper. Not much interesting comes out of Alberta, Canada, but this is one of those interesting papers that did. Okay, so we'll go back to full screen. Excuse me, I have a little scratchy throat today. Finally, there's no cloning theorem. The no cloning theorem, no perfect quantum copies of arbitrary quantum states are possible. Therefore, you cannot clone states. That is simply not true. What you can't do is clone states that are superpositions. So you can clone state A into another state A. You can clone state B into another state B, but you can't have some combination like they show in C. So even the diagram is not super clear here because it looks like you can't do A, B, or C. You can do A and you can do B, but you can't do C. You can't have some superposition of several different states that are cloned. The counterexample here, which I don't have time to go over, but I highly recommend this paper. It's called Long Range and Entanglement Generation via Frequent Measurements. Physics Review A is not going to get more reputable than Physics Review A. And what they said was, if you start measuring two different atom ensembles, for instance, and you start sampling them at the same time over and over and over, you're going to start entangling them. And as a matter of fact, that's exactly how they entangle in quantum computing. They start pinging these atom ensembles simultaneously, and you can use that to create entanglement. So not only is it no cloning theorem not true, but it's routinely violated in quantum computing. Okay, so what might we be able to do with applications? And this is what gets people excited about, oh, there's no communication, no action at a distance. Yes, you can have action at a distance. It's been measured. The Canary Island experiment measured it. And you might be able to use that, for instance, as a clock. So if you're routinely switching the spin state of one photon that's entangled within a photon somewhere else, the distance does not matter. It's an information wormhole, and that other photon will change states simultaneously. So that's what's nice about this being a clock. A frequency time standard is just a clock. Not only could it be a very accurate clock, but there's nothing interfering with the clock signal, because because they're simultaneously changing. So you could have a very good GPS conditioned atomic clock on Earth, and you don't need a big atomic clock on Mars or even on a satellite, for instance, because you could just have an entangled photon on that satellite or on that planet. So this would be very exciting for satellite manufacturers, and it would save a lot of gear. I can't tell you the number of clocks and complication on a typical GPS satellite, because they just want to keep track of what time it is. Here, you wouldn't have to. If you use quantum entanglement, you know what time it is. And so I think we're starting to see experiments with satellites. But right now, they're using it more for, I guess I'd call it encryption type applications. But here would be a really great application for timekeeping. Okay, remember that Herbertsmithite. If you broke that piece of crystal up and you separately entangled one piece and you separately entangled the other piece, once it's entangled, it's entangled. So then you could modulate, you break it up even more, you send half of a piece to Mars and you keep the other half on Earth. You can use it for signaling. You're modulating that quantum spin liquid with the magnetic field, and that modulation would then simultaneously appear on the piece on Mars. Isn't that communication? So you could do the same thing in reverse with a separately entangled crystal, where you're modulating the quantum spin liquid on Mars, and you're picking that up on Earth. Now you have a full duplex communication link. This would be very exciting, again, because it would be instantaneous. So it opens up a whole new series. If we can really do something like this, it would open up a whole new series of applications, such as avatars. You could imagine robotic avatars where you could get in to a robot station on Earth and physically feel like you're walking around on another planet without having to fly to the other planet. And it doesn't have to be a biological avatar like the movie. It can be just a simple mechanical robotic avatar. But imagine how beneficial that would be for space exploration, and how cost savings that would be in the long run if you could have that real-time communication link between different planets. Okay, final application that I had originally conceived of, which probably will not work the way I conceived of it, was power coupling. And this is where you would have a twisted light beam that if you could somehow break it in half, would you be able to use half the twisted light beam as a power coupling on a different location from the original beam? The problem with this, well, there's a couple problems. First, the OEM that I'm picturing here is twisted light that alternates back and forth. So out of the 20 spots of the twisted beam, 10 of them are orbiting one way, but 10 of them are orbiting the opposite way. So you're not going to get that Fujiwara effect like I described, where you have an overall momentum twisting. But say that you could somehow do that, get rid of the 10 that are twisting in the wrong direction and only get the 10 that are all twisting the same way, and you get the Fujiwara effect. You're still not going to be able to couple it into a quantum spin liquid like I'm showing, and use that quantum spin liquid to couple back into a beam like I'm showing. But even if you could somehow do that, it's an information wormhole. And to get inertial coupling backwards, say you're doing some work with the shaft and you're trying to twist that shaft, the inertia that you're trying to twist is being propagated through the shaft. To do that, you really need a space-time wormhole, not an information wormhole. So, for instance, if you had if you're somehow able to build a real wormhole, and you had entangled gravitons on one end, and you entangled them to gravitons on the other end, that could couple a twist of space-time through entangled states, then you could do it. So say, for instance, you have a Fontana gazer. It's a graviton laser. It's just a conceptual device. And you have this circulating in some kind of clockwise manner, these gravitons, or circulating in, for instance, a forward toroid. That's the kind of thing that you might be able to propagate through a wormhole. But just using twisted light is probably not going to couple power, because you have to have a way of coupling the inertia back through the wormhole. So that requires a real wormhole, not an information wormhole. So that's what I wanted to say about that. So that kind of concludes what I'd looked at originally in the 2012 to 2014 timeframe. But I did want to touch on a little bit work that's happened since then. So we'll go back to our list here, because some interesting developments have happened since then that might impact some of these applications. So we'll talk the Muschik 2013 paper first. This happened during this period, but I wasn't aware of this paper until it was pointed out to me by Jack Sarfati. Here's a picture of it. There's two different atomic ensembles that are in constant magnetic fields, and they can be, through this constant measurement technique that I alluded to earlier, they can be entangled. So 3 separate steps. We're entangling them. We're projecting a measurement on one of them that possibly destroys the state that's being teleported, and then we're recovering that state by this feedback mechanism. So this is a continuous quantum teleportation. This is one it's a dynamic continuous teleportation setup, and so I think that's significant. I think that's probably all I want to say about this paper, is that it's instead of discrete, it's a continuous scheme. So this provides for error correction, and this is going to be important for quantum computing. Okay, another one. We talked about the Susskind paper. There were a couple of interesting papers described by the Chinese in which 2 quantum memories are entangled. One over 50 kilometers, where something's changed in one memory and it shows up in a different memory 50 kilometers away. They are coupled, though, by a fiber optics. So you still need a fiber optics to maintain that quantum entanglement. There's another one later on that's only 12.5 kilometers apart. I think the title gives away the difference here. Entanglement of 2 quantum memories. And the later one is post-selected entanglement between 2 different memories or atomic ensembles. Post-selected, of course, just referring to a preconditioning of the probability function. That's a rat hole I don't want to run down today, but it's a more useful way of entangling, essentially. I think the most interesting recent one is this Dumitrescu 2022. And there's been a lot of coverage about this in the popular press. It's essentially a way to stabilize quantum memories for quantum computers. And this particular method uses a Fibonacci laser sequence. So why are they using the Fibonacci laser sequence? I made some notes because it wasn't super obvious to me. They're using rhythmic topological phase. They're needing to knot more than one time symmetry into the ion strand. They found if they were trying to ping this rhythmically, that they would decohere it. So they're trying to not decohere it. So this pulse train between these 2 different laser pulses turn into a Fibonacci sequence. When they use the Fibonacci sequence, they're able to get essentially different time symmetry out of these ensembles. So they're pinging A, and then they're pinging B, they're A, B, A, and then they're pinging A, B, B, A, etc. So that's a quasi-periodic sequence. And so this tends to manipulate the quantum ensemble in a way that helps stabilize it so that you can continue to measure it, and it's still getting refreshed without losing coherence. It's essentially a way to maintain coherence. So I think that's exciting because that means that, for instance, for a communication application, if we can maintain coherence over long periods of time, we could potentially stabilize this thing enough, even when we're changing the spin dynamics, stabilize this long enough to do useful communication between two different locations. So I think that kind of sums up the paper in a nutshell. I guess I'll open it to questions from you, Tim.
Do these open the door for instantaneous quantum communications? Because that's been described as impossible repeatedly, right? I get yelled at about that. So
I think if you look at that description I had of the Herbertsmithite, and you really believe that quantum spin liquid is all one qubit, and then you split it into two pieces, it's still one qubit. It's just in two different pieces now. You actually have to physically move that one piece. You have to send it to Mars physically. But when you do that, it's still the same qubit. So if you're manipulating the qubit and changing the state of the qubit in one location, that other piece of it, my way of thinking, that other piece of it should maintain the same dynamics. And so it should stay in sync since it's entangled. So if that's the case, then yes, we could do it for instantaneous quantum.
okay, well, and
it's
so
speculative, obviously.
Well, and then the other part too, and I saw you mention this, at least one of these methodologies was what you described as continuous, right? And so I think one of the challenges has been, this is something that bothers me, is like, okay, we have a single, atom, photon, particle of whatever kind, and maybe we can do one operation where we flip that at both points at once. That doesn't necessarily work for any kind of long-term solution. What you're talking about is continuous. So if you flip that entanglement, you can flip it back, you can measure it in both places.
Which would be the case for the clock application, right? For frequency time standard. And you would want to flip it at very periodic periods of time, so that you could use that for timekeeping and for a frequency time standard.
Yeah. Now, so you originally presented this for like Mars applications, and actually I think that's really interesting because so one of the things that intrigues me about it is right now we have remotely piloted drones, right? We know that approach to RPVs works. So we could do the same thing on Mars with the rovers, right? Right now we have that 4-minute light delay, but if we were able to somehow use this quantum entanglement, even if it wasn't a high bandwidth, we could at least control the rover in real time, as opposed to having to plan out where it's going to go to make sure it doesn't fall into a crater or something like that.
I completely agree with you. And we may be seeing evidence of that already with some of these UAPs. There's no evidence that there's any signals going to or from them. We don't see any signaling. So quantum entanglement may be one of the methods they're using to communicate with these UAP type drones.
Well, so let me also ask about, now you'd mentioned kind of a information wormhole versus a traditional wormhole. Could you describe that concept a little bit more?
Sure, yeah, and Susskind really touched on it best with his ER equals EPR discussion. That's saying that even if there's no space-time wormhole, that in information space there can still be a wormhole. And information space is is a broader application of the concept of space that includes all of the quantum variables. So these quantum states exist and are part of information space, and not all of them are associated with X, Y, Z, and T dimensions. There are other dimensionalities that are in addition to space. For instance, charge is a dimensionality. Angular momentum is a dimensionality. Spin is a dimensionality that is not necessarily tied to X, Y, and Z. So these particle spins can be synchronized, can basically share the same quantum information, and therefore there's an information wormhole between two particles. It's the same way of looking at the same. It's two different ways of looking at the same thing. You're looking at it as a shared qubit, or you're looking at it as an information wormhole where that quantum information is appearing in two different places at the same time.
Ah, okay.
So so it doesn't, essentially it doesn't care. The quantum states are superposition onto space-time, but they don't really care. There's no signaling going on necessarily. Once they're entangled, they don't care about space or time.
Yeah. Well, and I guess this next thought kind of goes way above my pay grade, right? But the idea was, you know, I keep hearing that C is the fundamental limit. Obviously, quantum entanglement seems to violate that. The thing that I've wondered about is that maybe because in a higher brain dimension or string dimension, maybe these particles are actually in the same place, even though physically in our dimension they've been moved apart and they're separated by, you know, 4 light minutes, right?
They're in the same states. I wouldn't say the same place, because place is space-time, right? Place is spatial.
Yeah.
Kind of get away from that and talk about states, which kind of reminds me of Shelley's work, come to think of it. State theory, where you're talking about the states of objects versus the place of objects. And so that is a different way to look at it.
Yeah. I think that was everything I had. Let me thank you so much for your time today.
Yeah, and thank you, Tim, for giving me a chance to present this on to a broader internet audience, because the audiences so far have been quite small for this kind of a talk. So I appreciate the chance.
Yeah, so that was our presentation. So let me before we do anything else, let's put our hands together for Mr. Gary Stephenson. A giant applause. Again, Gary is traveling today, and so we had to pre-record that. Hopefully we did an okay job. He kind of surprised me actually with the questions. I didn't know that he would have any questions at the end, so I just kind of had to wing it, which I'm not good at. But I am happy to do my best to answer questions on his behalf. So let me do this. I'm going to put this on speaker view, and I will take Jeremy Reese first. Sir?
All right. All right. So anyways, I'm broadcasting live, and I was hoping Gary was here because he had pointed out that the whole business of entanglement and some of the new developments. And another one I wanted to mention is in May of 2022 at the Oppenheimer lecture, Leonard Susskind spoke on a theory. You can look this up, the quantum origins of gravity. And in about 47 minutes, he talks about strange metals, which are a class of condensed matter physics, and related to these, quantum spin liquids like Fermi liquids and such. But he points out that condensed matter physics shows that these are topologically equivalent to extremal black holes. So these strange metals are which they made at the first one they made was at Brown a couple of years back, and they made it out of yttrium, barium, copper oxide. They took like superconductor ceramic material, and they put holes in it, and the holes in a grid pattern, and putting those holes in a grid pattern changed the quantum behavior of the material, from behaving like a spin half, to all the electrons behave like spin 1 bosons instead. And so there's some interesting things that can happen within new types of materials too. And I just wanted to point that out and ask if he had heard of it and what his thoughts were on it. But
okay, yeah, well, and thank you for mentioning it. And he may pick this up, in post, right, when he watches the replay of it. So Jeremy, thank you, sir. Did you have any questions I can help you with, or are you good for now?
Yeah, I'm good. I'm good.
Okay, I did have a couple of quick announcements because I'm wearing two hats for the next few minutes. So one of them is Bernie Conkin is with us in probably about an hour and a half. I'm hoping that he can share basically an LENR update, and that's something that we want to try and get into as well. That's something that we totally neglected in the past. There's some overlap there though, so you know that's absolutely Bernie's department. He has been with this conference for a very long time, so we're hoping that we can work him in. He has a couple of scheduling holdups. Also, Phil had asked about the hover coil. That's a fellow named Gerald. It's a friend of Jeremiah Pop. He was going to demo that. So I've emailed them. They were talking about it. If they are able to attend, I would love to have him demo that. I mean, you know, again, I've been telling him for quite a while, bring it, show it. So let me see. Actually, Jeff Rainier, Jeff, you did have your hand up, sir. Can I answer your question?
Sure. Yes. I kind of have an odd question. I've been looking at kind of like, can you interfere with quantum entanglement? You know, can you use a laser pulsing to do that?
It sounds like you can, right? I mean,
Yeah, so if you had UAVs or UAPs, they're using quantum entanglement, then it would be, why not try to take one down? Why not
yeah.
try to interfere with the communications?
Well, and so what Gary was saying was they had to apply that Fibonacci sequence so that they didn't disrupt entanglement, right? So
right, so you could turn around and try to, you know, disrupt entanglement. That's my point.
yeah. I think there might be a possibility there. I mean, one of the, if I could just, again, I'll walk you guys through kind of the for me, this has been something superluminal communications, especially with quantum entanglement, has been something that I've been really interested in for the last few weeks. There were a bunch of articles on quantum communications that came out online. And when I started to look into it, I naturally assumed, I was like, well, look, entanglement operations happen instantaneously. So someday this will be useful for instantaneous communications. And I was immediately met by mainstream physicist types who said, no, that's not true, you know, because of the measurement and all that. So that was how I ended up connecting with Gary. Gary did point me towards Leonard Susskind, who has not responded. I would love to interview him. And he actually pointed me towards Kent Peacock, and we're doing something on Monday. And Kent, Gary referenced him. He did a bunch of, he did a basically a philosophical statement explaining why instantaneous communication is possible. So the things that I like about it are quantum entanglement, some kind of communication based on that explains UAP communication. And I think it solves, or it could solve, the Fermi paradox, right? I mean, SETI is out there looking for radio signals from the stars and they haven't seen a whole lot. Well, I think it's likely that radio communication is something short-lived and that advanced societies move on to something better. And hopefully that's quantum communication of some kind. So yeah, so there's a lot to be said there. Let me see, I think Jared had his hand up too. Jared? No? Okay. So again, it's option Y on Mac or Alt Y on Windows. If you guys have any questions that I can answer, I am certainly not a genius on this. My own gut feeling is that quantum entanglement, somebody had said this, that everything that happens in our universe comes from forces, like when particles interact, when they directly touch, right? Even photons, you have an energy packet that gets transmitted. And so with something like entanglement, you know, it seems like spooky action at a distance. My gut feeling is that these particles are next to each other in higher brain space. That's what my gut feeling is. And So I think that it may not obey the standard rules of relativity theory because, you know, in a higher dimensional space, maybe it is relativistic, but they're touching, right? And that's again, I know I'm way out on a limb there. That's just what my intuition says. So.